When a natural gas stream is first produced, it often consists of a number of different hydrocarbon gases. Depending on what they are, these gases can be classified as light or heavy. The percentage of each gas and the availability of markets for these products determines whether the hydrocarbon products should be separated. Efficient separation of the components can be accomplished by a number of different methods, including the method we'll be looking at in this module: chilling the gas stream to very cold temperatures. Chilling transforms some of the gases into liquids, which can then be separated from the lighter gas. In this program, you will see some of the reasons for separating natural gas liquids, also called NGLs, from a gas stream. We'll look at common methods for chilling gas to separate the liquids, and we'll see how the application of very low temperatures to a gas stream, commonly called cryogenics, affect liquid separation. Prior to viewing this program, you should have successfully completed the modules titled Basic Principles of Pressure and Temperature, Centrifugal Compressor Principles, and Heat Exchanger Principles. Now, if you haven't, you may want to study these programs before proceeding. One other thing before we continue. Cryogenics deals with a wide range of temperatures, and especially extremely cold temperatures. Keep this in mind when you're working around a cryogenic plant. Your safety is very important during all operations. This is the first section of a three-section module on cryogenic principles. In the first section, we'll look at natural gas components, economics of liquid separation, gas chilling, the definition of cryogenics, and the cryogenic process. Natural gas streams include different types of hydrocarbon gases. Now, the exact percentage of each hydrocarbon gas in a natural gas stream varies based on production region and on temperature and pressure of the gas stream. Hydrocarbon gases are generally described as either light or heavy. Hydrocarbon molecules are composed of hydrogen and carbon. This weight description, light or heavy, commonly refers to the number of carbon atoms in each gas molecule. Light gases have a small number of carbon atoms, while heavier gases have more. The remainder of the hydrocarbon molecule is hydrogen atoms. So, listed from lightest to heaviest, the components of natural gas are methane, ethane, propane, butanes, pentanes, hexanes, some heavier components, and liquid condensates. Methane is the lightest hydrocarbon gas, and it often makes up the highest percentage of the natural gas. This gas, mixed with some ethane, is a typical gas which reaches a transmission line for sale. The value of a natural gas stream, in terms of dollars, is determined by two things. First, how much of each type of gas the stream contains, and second, the demand and availability of users for the individual components. Now, in some locations, this means selling the dehydrated gas containing many different components as a single product. For other markets, it means liquefying and separating the heavier gases from the methane, then selling the liquids as separate products. Now, always keep in mind, the more processing you do to a gas stream, the higher the operational costs are going to be. What we're looking for is the least expensive and most efficient way to process the gas stream. Now, several different processes have been used to liquefy and separate heavier gases. The most common processes in the gas industry are lean oil absorption, refrigeration, and cryogenics. The appropriate process for a facility is determined by the makeup of the natural gas stream, available gas pressures, and the market for separate products. Lean oil absorption is one of the oldest separation processes that is still in use. In this process, when the lean oil comes in contact with the natural gas stream, it absorbs the heavier hydrocarbons. The oil, rich with trapped hydrocarbons, is stripped to recover the heavy hydrocarbons and prepare the oil for recycling. The heavier hydrocarbons are recovered by warming the oil mixture. Because of the high energy requirements, lean oil absorption is not very energy efficient, and therefore it's relatively expensive to operate. 90 to 95% of the propane and 98 to 100% of the heavier hydrocarbons can be separated and recovered with this method. Lean oil absorption, however, recovers little or none of the ethane. Another separation process that's been in use for many years is refrigeration. In the refrigeration process, the natural gas stream passes through a chiller. The chiller basically does the same thing that your home freezer does, only it uses slightly colder temperatures. The chiller cools the natural gas to a temperature range of 0 degrees Fahrenheit to minus 20 degrees Fahrenheit, using either propane or freon as a refrigerant. Chilling causes the heavier hydrocarbons to liquefy. Then they can be separated from the gas. Compressing the refrigerant and driving the condenser are the major energy requirements of refrigeration. Compared with lean oil absorption, refrigeration uses less equipment and energy to recover similar amounts of heavier hydrocarbons. Refrigeration separates about the same volume of propane and heavier hydrocarbons as lean oil absorption does. In addition, it can recover small amounts of ethane. Cryogenics is the newest and most energy efficient of the three processes. In the cryogenics process, the natural gas stream is cooled to extremely low temperatures, in the range of minus 50 to minus 150 degrees Fahrenheit. Instead of using a refrigerant, cryogenics uses a mechanical method to cool the gas which liquefies the ethane and heavier hydrocarbons. The liquids are then separated from the methane. Cryogenics does require additional compression to raise the pressure of the methane. However, when compared to lean oil absorption and refrigeration, cryogenics has moderate energy requirements. Cryogenics can separate and recover similar quantities of propane and heavier hydrocarbons as lean oil absorption. However, unlike other processes, which can recover only up to 25% of the ethane, cryogenics can recover much higher amounts, 80 to 95% of the ethane. To summarize, when you look at the energy requirements for the three processes and the amount of recovered hydrocarbons, in particular ethane, cryogenics stands out as the most energy efficient method for recovering more NGLs. Now let's take a minute to talk about gas chilling. Whenever gas is cooled sufficiently, liquids begin to form. You see a good example of this process when you fill a glass with ice and liquid. When warm, moist air contacts the cold glass, it is chilled, causing water vapor to condense on the outside of the glass. The temperature at which water vapor condenses out of the air is called dew point. Now the same process occurs when natural gas is chilled, or when the dew point of natural gas is reached. Some of the heavier hydrocarbon gases condense and separate from the gases. If natural gas is chilled to a very low temperature, for example, minus 150 degrees Fahrenheit, much of the ethane, almost all of the propane, and the heavier gases will condense. The methane, being lighter, will remain as a gas. However, the chilling process will trap some of the methane in the liquid. NGLs with a high methane content are not marketable. Therefore, the trapped methane must be separated. Gas chilling operations maximize the amount of ethane or heavier hydrocarbons liquefied, but minimize the quantity of trapped methane. The quantity of methane which remains trapped during the chilling process depends on several factors. First, the pressure and temperature of the chilling system is very important. Less methane will be trapped at less pressures. Second, the rate at which chilling takes place is also a factor. More methane will be trapped if the temperature is reduced very quickly. Now, the third factor is the mechanical efficiency of the vessel, which separates methane from the liquids. If the separation process of methane from liquids is too warm, not only is the methane released, but so are some of the heavier gases. Now, there are three methods to chill natural gas: refrigeration, pressure reduction, and expansion. Each method operates in a specific temperature range. In refrigeration, an external refrigeration system using either propane or freon chills the gas stream. The temperature range for refrigeration is 0 degrees to minus 20 degrees Fahrenheit. In pressure reduction, a pressure-reducing valve called a JT valve reduces the pressure of the gas stream. The reduction in pressure causes a reduction in temperature in the range of minus 50 degrees to minus 70 degrees Fahrenheit. In expansion, the gas stream passes through an expander compressor. An expander compressor is a device which has two separate units, the expander and the compressor. These units are separate, but share a common shaft which transfers energy from the inlet gas in the expander to the compressor, where the gas stream returns to the expander compressor downstream in the process. Gas at a given temperature and pressure contains energy which is in the form of heat, pressure, or velocity. As gas flows into the expander side of the expander compressor, the pressure drops. The flowing gas turns a wheel in the expander. Energy to turn the wheel is removed from the expander inlet gas and is transferred to the gas being compressed in the compressor. The combination of gas expansion and removal of energy produces very low or cryogenic gas temperatures in the range of minus 100 degrees to minus 150 degrees Fahrenheit. As we talked about before, cryogenics involves very cold temperatures in the range of minus 100 to minus 150 degrees Fahrenheit. A gas leak or exposure to metal surfaces at these temperatures is extremely dangerous. You can be severely injured while working with cryogenic equipment. So please, when you're operating around units utilizing cryogenic temperatures, you must be careful. Cryogenic processing of a natural gas stream involves three basic steps: dehydration, chilling, and fractionation. Dehydration is the removal of water from a substance. Because of the very cold temperatures in cryogenic processing, almost all the water vapor must be removed from the gas stream. Any water vapor remaining will form hydrates, which can damage equipment and even stop the flow of gas. Dehydration uses the processes of absorption and adsorption. The term absorption means the removal of water vapors from a gas stream by contact with a liquid desiccant. An example of a liquid desiccant would be glycol. Natural gas and glycol come in contact, and the desiccant absorbs the water from the gas. Adsorption is the removal of water vapors from a gas stream by contact with a dry solid desiccant. A dry desiccant is a solid granulated material which has an attraction for water. An example of a dry desiccant would be silica gel. As gas flows through a bed of these granules, the water attracts itself to the surface of the granules. The granules adsorb the water. A liquid desiccant can reduce the dew point of gas to as low as minus 30 degrees Fahrenheit. If the gas must be drier, dry desiccant dehydration is used. Dry desiccants